Section 1.4, Penetration and Shielding. First, let's review the Polyexclusion Principle. It states that no two electrons in the same atom can have the same set of quantum numbers. It tells you each atomic orbital can accommodate up to 2 electrons with different spins. For a many electron atom, such as helium, the order of the energy levels in each shell is S lower than P, lower than D, lower than F. For example, when N is 4, we have 4s orbital with lower energy than 4p, lower than 4d, lower than 4f. The reason why the 2s orbital has lower energy than the 2p is because part of the 2s orbital is very close to the nucleus. It's called penetration. The nucleus electron attraction for the 2s electron is more negative than for the 2p electron. Therefore, the 2s orbital has lower energy than the 2p orbital. For the same reason, we have this order for 2s, 2p, 2d, and 2f. So this is a picture that shows you the radial distribution functions of 2s and 2p behave slightly differently. This is the 2s, the blue curve, with a significant portion close to the nucleus, with R very close to 0. So you compare this function versus this function. Now, electron shielding in a many electron atom, such as a helium atom, in quantum mechanics, if you have 2 electrons, it's called a many electron system. So every electron is attracted by the nucleus. It's also repelled by all other electrons. The repulsion from all other electrons partially cancel the attraction from the nucleus. And this repulsion is called electron shielding. So for example, in a helium atom, you have 2 electrons occupying the 1s orbital. So each one repels the other. And that will reduce the effective nuclear charge. The nuclear charge of the helium atom is 2. And because of the repulsion between the 2 electrons, there is an electron shielding of roughly 0.35. Therefore, the effective nuclear charge felt by each electron in the helium atom is roughly 1.65. How can we calculate the electron shielding for other atoms? It's pretty simple. You look at the number of electrons in the same shell. The number of other electrons in the same shell. Do not count the electron of interest because it does not repel itself. And then 0.85 times the total number of electrons in the n-1 shell. And then if you have electrons in the n-2 shell or lower shells, their electron shielding is 100%. So this electron shielding is exactly 1. Let me give you a few examples. Nitrogen. Nitrogen has this 1s2, 2s2, 2p3 electron configuration. Now let's look at the valence electrons. There are 5 valence electrons here. For any of the 5 valence electrons, it feels repulsion from the other 4 valence electrons in the same shell. So it's 4 times 0.35. And this is the n-1 shell. The n-1 shell contains 2 electrons. So 2 times 0.85. So this is 1.4, this is 1.7. Together you have 3.1. So the electron shielding for each valence electron is 3.1. What about the effective nuclear charge? The total nuclear charge is 7 minus 3.1. you get 3.9. So this is the effective nuclear charge. This is an indicator of the attraction felt by the electron. Now let's look at another example, fluorine. Now we have 7 valence electrons and 9 nuclear charge. The electron shielding, this time we have 7 valence electrons, so each is repelled by the other 6 times 0.35. In the N-1 shell, there are 2 electrons, so 2 times 0.85. So this is 2.1, this is 1.7, together 3.8. The nuclear charge is 9 minus 3.8, we have 5.2. So the valence electrons in the fluorine atom fills this 5.2 effective nuclear charge. So that means the valence electrons in fluorine are more attracted to the nucleus than in nitrogen. That means the ionization energy of fluorine is higher than the ionization energy than nitrogen. It's more difficult to remove an electron from the fluorine atom. One more example, this time aluminum. Now we have 1s, 2s, 2p, 3s, 3p. Now look at this shell. This is n equals 3. So 3 electrons, 3 valence electrons, and then each is repelled by the 2 other valence electrons, 2 times 0.35. And over here, N-1 shell, we have 8 electrons. N-2 shell, we have 2 electrons. So put them together, we get 9.5. The effective nuclear charge is 13. This is the number of protons. Minus 9.5, we got 3.5. So aluminum has a smaller effective nuclear charge than the valence electrons in fluorine. And also, that's also very important, this is shell 3. Fluorine has shell 2. So the distance between these valence electrons and the nucleus is greater than the distance between the valence electrons in the fluorine atom to the nucleus. Both reasons make a contribution to the fact that aluminum has a much smaller ionization energy than fluorine. It's a lot easier to remove an electron from the aluminum atom than from the fluorine atom. Again, this is because in the aluminum atom we have smaller effective nuclear charge and a longer distance from the nucleus. Now let's look at the table of effective nuclear charge, and you can see the trend here. Let's look at lithium. Let's look at the valence electrons. 1.28, 1.91, 2.4, 3, 3.8, 4.5, 5.1. So going from lithium to fluorine, we have larger and larger effective nuclear charge. It's more and more difficult to remove the electrons. Same here, 2.5, 3.3, 4.1, 4.3, 4.9. Over here, again, it's more and more difficult to remove the electron from the atoms from left to right. If you look at the core electrons or inner shell electrons, well, the electron shielding is pretty small, because the 1s electron is not shielded by the 2s or 2p electrons. It's not shielded by 3s, 3p, or 3d electrons. So if you look at the sodium, look at the 1s electron of sodium, it's close to 11. This is close to 11, close to 12, close to 7. So really, in this 1s orbital of sodium, it's the electron shielding comes from the other 1s electron. So this is 11.0.35, 12 minus 0.35, 13 minus 0.35, and so on. But of course, the equations I showed you before, they are just approximate equations. These numbers are approximate numbers. They are not exact numbers. They just give you a rough idea of how much the electron shielding is, approximately. Alright, so now let's look at the energy levels of many electron atoms. 1s orbital, and then 2s. 2p has higher energy. 3s, 3p, 3d, I don't know. So if you compare 3D with 4s, sometimes 3D has lower energy, sometimes 3D has higher energy. It depends. Alright, and then 4p, 4d, and 4f. Now in this picture, again, we're talking about atoms. So now you're looking at this 1s orbital, 2s, the red line is 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p. And there are exceptions over here. You can see sometimes the 3d atomic orbital energy is greater than the 4s atomic orbital energy. Alright.